again, minor glitches. This means it's going to be a great presentation. So anyway, back to where I left off. The whole basis of the presentation that I'm going to give this morning is based on the question of what is a tornado and how do we know in the context of QLCSs. So I'm going to begin with a two-part motivation. Here we go. The first part is based on a childhood trauma. So you see here on the left is base reflectivity, on the right base velocity from a QLCS and a fairly classical progressive QLCS that occurred in northern Illinois and northern Indiana on May 18, 1997. You see this initial upscale growth from several HP supercells in north central Illinois, and this classical growth into a progressive QLCS. And at the time this event occurred, I was living in the south suburbs of Chicago as a 7-year-old child who was actually very, very scared of storms at the time. So when this moved into our neighborhood, back around, it was around 8:15 that night, I wasn't too happy. Ended up getting rushed in the base, and you can see on the left is base velocity, on the right is storm relative velocity. You see a circulation on the left side of each panel that moves right through the neighborhood, and you can see the yellow dot, which where I live with my parents, my grandmother, and my sister. And we had a string of damage that went right through our subdivision, about a half block south of our house. You can see the yellow damage points. Those are the damage points I could retrace via newspaper clippings and memory from the event. The damage was fairly substantial in some places. You had some roofs torn off of homes, some damage to businesses, etc. And the path of damage through our neighborhood was about 50 yards wide. And so you can see in the newspaper clippings there, I highlighted that the National Weather Service came, surveyed the damage, and initially called it a gust front, which there were quite a few people in the neighborhood at the time who actually claimed to have seen the funnel. And later in storm data, it was revised as being assessed as a potential F0 to F1 gustnado. So this question of what is a tornado in the context of QLCS has actually been something that's been percolating in my mind for a while. What is a tornado and how do we know in the context of QLCSs? And then the second part of the motivation for why I've been really particularly interested in this question dates back to about 6 years ago, 5.5, 6 years ago now. It was June 30th, 2014. So it's the double derecho event across the southern Great Lakes and the Corn Belt from central Iowa across northern Illinois, northern Indiana. And I happened to be home visiting my parents on this particular weekend before this, and ended up on the survey team for the Kankakee River Valley south of Chicago as those two mesovortices moved through it. And when you see something like that on the radar screen, that Michael Scott faces, pretty much sums it up. So Ricky Castro and I, Ricky Castro from the Chicago office, and I went on the survey in the Kankakee River Valley, and were presented with quite a challenge. We were getting directed around by several EMs and had a list of damage reports. And each site we went to, each discrete damage location we went to, at least for the first several hours of the survey, seemed as though the damage was tornadic in nature when we arrived there. The damage locations often featured EF1 damage or even close to or approaching EF2. The damage locations were discrete, meaning that if you went, say, north-south along the given road from the damage locations we were surveying, you'd reach farmsteads maybe 100, 200 yards away that had no damage whatsoever. And then you'd go another mile and there'd be another farmstead with significant damage. So it was clear to us that we were dealing with what appeared to be tornado damage. Again, and much of the damage was also clearly convergent or cyclonic convergent in nature. But what wasn't clear to us, given how the damage was spaced out and located, was which tornado produced which damage. We were basically given all these sets of damage points and had to sort out which damage was linked to other damage located along the paths of these mesovortices. And that took about 2 months of sorting through the damage data, sorting through radar data, consulting with experts, and this was the assessment we eventually came up with in time for storm data publication, for the publication of June 2014 storm data. And there were some things that we felt were not necessarily, there were some inconsistencies and uncertainties, but we felt at the time that given the information that we had, which is everything you see on the background of the maps, that all the dots, that's the best we could do at the time. And so that's when we ended up publishing 14 tornado tracks. All of them we ended up rating initially as the F1. And then about a year and a half, 2 years later, I was going through Google Earth and went through and said, I just wonder what could be seen in the Kankakee Valley after this event. Google Earth had been updated in May of 2015 with new imagery. And on the top panel there that you see the outline in green of one of the official tornado tracks that we had entered into storm data. And then if you look carefully at the satellite imagery, you'll notice that there's 2 tree lines that fall between the white hashes there. The first tree line was about a half mile from a road where we did a ground survey from. And from that road, all we could see was that there were trees down. Couldn't necessarily tell exactly which way they had fallen because they were so distant from the road. We could not make anything out from the second tree line, and we could make out some of the piles of debris in the distant field from the damaged outbuildings. So when you look at the satellite imagery, you can see a clear-cut path cutting through the 2 tree lines. And you notice that in the one tree line that had the most mature trees and wasn't cleaned up at the time of the imagery collection, you can actually see the trees having fallen in a southeast to east-southeast direction. And so seeing that was kind of an uh-oh moment, knowing that the initial assessment of the tracks was probably not correct. And so we spent another 2 years going through a whole bunch of Google Earth image locations, and we added 500 additional, or over 500 additional information points, both areas where we found damage or evidence of damage in Google Earth, and areas where we found a complete lack of evidence of damage. And we came up with this reassessment of the tornado tracks. We actually combined some of the tornado tracks together in the southern mesovortex, and then we basically completely reassessed the northern mesovortex, and it's a really complicated pattern of damage. So to publicize these changes to this event and explain how we came about formulating them, we wrote this article that we submitted in July of 2018 to EJSSM, going through and describing the process and the uncertainties in the process of reanalyzing this damage. And after a long and sometimes occasionally contentious 13-month review process, the paper got published back last August. And if you read through, EJSSM publishes the major comments in the review process. There's one comment that came up in the last round of reviews from one of the reviewers who had been arguing back and forth to some degree about the actual nature of some of the damage that we had witnessed in the surveys. And the final statement made on this topic is essentially that identifying or classifying this damage is a taxonomic exercise, and the question of what is a tornado probably needs to be revisited in the literature to distinguish some of the tornado events from this study from quote-unquote more accepted QLCS tornado definitions or events. Now, from my point of view, my perspective, the first thing I wanted to do, of course, was make sure that I had a listed definition of what is or isn't a QLCS tornado, and in fact, there is no formal definition of or special definition of what a QLCS tornado is. So the more accepted version of a QLCS definition or tornado definition kind of fell to me. I didn't exactly understand what that was getting at versus what we were looking at. But I do think it's a valid point to raise that it might be time to reassess how we define what a tornado is in general. And so if we're going to do that and we're going to reassess what the definition is of a tornado or perhaps clarify it or constrain it, we need to understand what factors should be considered and what some of the challenges might be to that. And so that's what the basis for the rest of this talk is going to be. And so we need to begin by identifying what the challenges are in damage classification and classifying what a tornado is. And in particular, in the context of QLCS is where this question most frequently comes up. So I'm going to identify three challenges. The first one is, I think, a very familiar one to anyone who's ever worked at QLCS event, and that's that these tornadoes are usually moving very fast. So I'm not going to belabor this point a whole lot, but I do like to use these visuals as kind of an illustration of the challenges of translation pose. So, for instance, let's say we have a hypothetical scenario. We have a tornado that has an inflow velocity or radial velocity of 7 meters per second, and you can double that to estimate knots, so about 14 knots, and a tangential or rotational velocity of 20 meters per second or 40 knots. Let's say that it's moving from left to right or to the east across the screen at 25 meters per second or 50 knots. So 58 mile an hour forward motion, that's definitely within the realm of QLCS possibility, right? If you vector add those three vectors at 4 different points along the radius of maximum wind, that's what your wind field would look like. In this case, this tornado or this vortex would not have a closed circulation in its wind field. Right? And if you take that vortex and you move it through, let's say, a cornfield or a forest, this is one potential damage pattern that could arise from that. So, the first thing you'll notice is that, again, there's no tight circulation in the damage pattern, right? It's a convergent damage pattern, which I think many of you have seen on damage surveys. If you're looking at just one plane in the east-west plane, it's going to look like all the damage is generally occurring in one direction, right? Sans the north-south convergence signature. And the other thing you might notice is if you look at the very bottom of that figure, this is actually a strong F1 or EF1 tornado. Right? This is a 103 mile an hour maximum horizontal wind that you would derive from the combination of the translation, the rotation, and the inflow. So this is not a really weak or low-end vortex, essentially. This would be a mid to upper-end EF1 tornado that you'd be looking at. So translation can pose some obvious challenges in terms of identifying the causal mode of damage within a QLCS. I think everybody understands that pretty well if you are familiar with QLCS events. You're, again, familiar with that. Perhaps a bigger challenge is that mesovortices can produce damage in different ways. So on the left here, you see this is a pretty clear tornado signature. This is from a strong tornado we had that down here in December, west of Huntsville. So the killer tornado, and you see the tornado debris signature. Not much question as to what's causing the damage there. But that's not the only way you can get damage associated with mesovortex. If you go back to some of the work that occurred from the BAMX field campaign in 2003 and some of the results from that campaign and from other studies after that, you notice that there are some emphases on other damage causes associated with mesovortices. And one in particular is when you have a mesovortex and you have a rear inflow jet descending to the surface behind the mesovortex and along the side, rightward side relative to the forward motion of the QLCS, you'll notice that if you juxtapose the momentum with the descending rear inflow jet and the pressure gradient force associated with the mesovortex, you can get some particularly strong or intense winds and damaging winds. Associated with the mesovortex is not tornadic or not necessarily tornadic or thought to be tornadic in nature. That would be the example on the right here in this illustration from Atkins and St. Laurent 2009, where you see the momentum of the rear inflow jet juxtaposed with the mesovortex. So mesovortices can produce both tornadic and seemingly non-tornadic wind damage. And I say seemingly because the third challenge associated with classifying damage from QLCSs can actually, I think, throw a lot of that into question. So there's no doubt, I think everyone's familiar with the idea that the definition of what is or isn't a tornado is kind of vague. If you forget the exact wording, it's here on the screen. For those of you who like to decide or joke about the violently rotating column of air, that's actually not even in the definition of a tornado anymore, according to the Amos law. So it now just has to be a rotating column of air in contact with the surface, pendant from a uniform cloud, and often visible as a funnel cloud with circulating dust or debris at the surface. So I go back to this previous slide, and we need a rotating column of air. So your mesovortex is a rotating column of air. It needs to be in contact with the surface, and so if there's wind damage occurring at the surface associated with the vortex, then the vortex is by definition in contact with the surface. It needs to be pendant from a cumuliform cloud. The way I read that is that the circulation has to extend at least up through cloud base. So if you have a mesovortex, it's going to, in all likelihood, extend right up through cloud base. And then the visual there, the funnel cloud or circulating dust or debris is kind of an optional tag at the end of the definition. So just by the definition, the vagueness of the definition of a tornado itself, I'm not even exactly clear on how these scenarios to the right would necessarily be excluded, even though it's in literature written as non-tornadic damage or non-tornadic processes. And I think there are some valid physical differences between what you see on the right in terms of the generation of damage and what's generating damage in the radar screen on the left. So that poses kind of one final overarching question within these challenges to how does a QLCS mesovortex produce a tornado? Or maybe even a better question for these leading edge meso or mesovortices, at what point does a mesovortex maybe become a tornado, right? So those are the three challenges of the broadness of the definition, the vagueness of the definition of what is or isn't a tornado, the fast translation of these vortices, and the fact that you can have different processes associated with the mesovortex producing damage. These three challenges are all things that would have to be kept in the forefront, really, when trying to decide or determine if there's a way to better clarify what is or isn't a QLCS tornado. And so, how that then leaves the next question: how might we constrain the definition of a tornado, and what issues could arise from attempting to do so? So we've outlined kind of the challenges in terms of determining what is or isn't a tornado. Now, how might we apply those into actual constraints on the definition of a tornado? And I'm going to discuss two different possibilities that are both rooted in peer-reviewed literature. The first is a definition of a tornado, a proposed definition that was provided by Joshua and Karen Tasiba in a paper that was published in Monthly Weather Review in 2013. So the part I want to focus on here in the definition on the right is this idea of the vortex intensity. So they have the other constraints in the definition they have are looser constraints, but they really focus in on the rotational velocity of a vortex. So they want a maximum wind velocity difference. This would be a delta V across the column of rotating air to exceed 40 meters per second. So in more common parlance, this would be a rotational or tangential velocity of 20 meters per second, or about 45 miles per hour. So if we were to use the Warman and placebo definition, you'd have to determine whether or not the column of air or the vortex that you're surveying reached a rotational speed of 45 miles an hour along its track, and if so, that would be how you would define it as a tornado. If you determine it didn't reach that rotational velocity, then it would fail to meet that criteria. I'm going to pose that there's a problem with this, though. So you would need to identify the rotational velocity in most cases from a damage survey. You'd have to do that. You wouldn't be able to, in most cases, have mobile radar data near the surface available to you. So that wouldn't be that particularly strong of a challenge. And you could infer that by finding the EF scale estimated wind speed along the survey, which you're doing anyway. If you're out there, you're trying to estimate what the maximum wind speed is based off the damage, and then you would have to back out the translation essentially, because the definition is not rooted in the maximum actual wind speed of the damage. It's rooted in the rotational velocity of the damage. Right? So you basically have to take your EF scale estimate, subtract how fast the vortex is moving to get the rotational speed that would then determine whether or not the vortex met tornado criteria. So there's really two potentially big problems in this. One, translation would eventually play the key role in event type identification. So in the plot on the right, I have translation on the x-axis, and I have essentially what would be your survey estimated EF scale derived maximum wind speed estimation on the y-axis. And for any event, you'd have to go out, you'd have to estimate the translation, and then if you look at the EF wind speed, it would have to meet or exceed the wind speed along that purple diagonal line for that vortex to meet the definition of tornado. So for instance, a vortex moving at 25 miles an hour, you'd have to have a maximum wind speed of at least 70 miles an hour for that vortex to be considered a tornado. Anything less than that, anything below that on the diagonal line would not be a tornado. Anything above it would be a tornado. So that's fairly straightforward. But the potential here is that we really play havoc with the QLTS tornado climatology. Now, why is that? Well, let's consider two breakpoints here. That first arrow is the first yellow arrow on the left would be the criterion point to have a vortex be considered a tornado if that vortex is moving at 40 miles per hour. At 40 miles per hour, you see that breakpoint is 85 miles an hour. So your wind would have to be 85 miles an hour or stronger to be considered a tornado by this definition. In essence, once a vortex moves at 40 miles per hour faster, you could never have an EF0 tornado. And if you look at the second arrow, that's at 65 miles an hour. That's the breakpoint. 65 miles an hour, your minimum wind speed would have to be around 110 miles an hour. So once you get into these cases, especially those that we see down here in Dixie sometimes, where we can have QLTS moving 65, even 70 miles an hour on occasion, you would never be able to have an EF0 or an EF1 tornado. Your vortex would have to be EF2 intensity to even be potentially considered as tornadic in nature. So vortex intensity, while it might make some sense in terms of we don't want to really every little vortex to be considered a tornado, it could pose some real big problems to the overall climatology of tornadoes especially the eastern half of the United safe if we went this route. So the other potential defining characteristic would be the vortex that we could use to constrain the definition of the tornado would be vortex structure. So this is sort of the stuff that comes out of Kevin Skow's work, basically taking the swirl ratio of a vortex, which is estimated as the tangential over the vertical motion of the vortex, and determining whether or not the vortex meets this swirl ratio criteria of what is a tight, concentrated vortex near the surface. So in theory, swirl ratio less than 1, you don't have those streamlines through the vortex reaching right to the center of the circulation near the surface, so you don't have a tight, compact circulation. Once you reach a swirl ratio of 1 or more, you do have the streamlines reaching to the center of the circulation. You have a tight vortex center, and of course, swirl ratio greater than 2, you now have a 2-cell multi-vortex circulation. So in practice, what of course Kevin Skow did in the 2017 paper from the Central Iowa case in August of 2014 was take numerous circulation tracks and largely based off aerial imagery, estimated what the swirl ratio was. So like in Channel A, for instance, estimated that as a low swirl ratio vortex without a tight defining path, circulation path, and therefore I'll call it a mesovortex and not a tornado, versus channels B, C, and D, B and C being clear vortex paths, tight vortex paths, price swirl ratio between 1 and 2, and then channel B appears to be a potential multi-vortex path, swirl ratio greater than 2. So, I mean, from a physical science perspective, from my personal perspective as a physical scientist at least, this would make a lot of sense to have a physical constraint based on the actual structure of the vortex itself. And so, in theory, I'm actually quite a fan of thinking of this in the swirl ratio perspective, where there might be a few issues, though, in terms of using swirl ratio as a defining factor, a defining characteristic, is the applicability, the ability to apply it universally in the field. And so I'm going to use one example of how this might be an issue. So this is from a tornado outbreak we had here in North Alabama back in November 2016. The high top radar is just off the upper left of the panels here, so we're very close to the HTX 88D radar in Northeast Alabama. You see reflectivity, velocity, spectrum width, and rho HV is your CC there in the lower right. You notice the circulation here, so very weak circulation and base velocity. As we go forward in time, you notice that this very weak circulation does top a lowering in rho HV or CC. And both the circulation, as weak as it is, and the lowering in rho HV or CC are persistent through time. So a few days after this event, this was a major outbreak. This was actually the very smallest part of a major outbreak here in North Alabama. But so a couple days later, I went out with Todd Barron, who's the WCM there, well, he's the MIC now. He was the WCM at the time. And we looked at this circulation track. And the damage along this track, admittedly, was very weak. I'm showing you the 3 pictures that encapsulate the worst damage we found. So you see some large tree limbs down. You see some tin peeled back on a very old barn. There's some hay bales right at the bottom of that picture. Those were gently rolled down a hill and rested up against the side of the barn. And then a power pole that was very rotted out near its base was quote unquote broken and tipped over. So this was some really almost impressively weak damage. But the path of damage extended for about 3.5 miles. It actually cleared an almost 1,000-foot mountain, cleared Little Coon Mountain here in northern Jackson County, Alabama. And so ultimately the determination was that we can call it a low NDF0 tornado based on the combination of the damage being a continuous narrow track, and we had the circulation being picked up by high top, and we had, of course, some evidence of debris being wafted by the high top radar. But my question I pose in relation to using swirl ratio as a determining factor to define a tornado is how would you even begin to estimate swirl ratio in this situation? Did we have a swirl ratio of greater than or equal to 1 associated with this vortex? And you might say, well, you had debris being wafted, so you probably did have at least some sort of tighter surface circulation, right? Well, maybe, maybe not. If you look at some of those pictures from the damage survey, you notice leaves, right? This is late November in North Alabama. There are leaves everywhere on the ground and some still left in the trees. So it could be very conceivable that the leaves were the only reason why we were able to trace any debris into this circulation. But again, we can't really say that. We don't have a crop field, or even in this case, any sort of clean, clear-cut track through a stand of trees to say that the swirl ratio likely reached 1 or more. So vortex structure, while theoretically I think makes a lot of sense in terms of defining what is or isn't a tornado, could be really hard to apply practically in a lot of situations where you don't have a clean, uniform tracer in your damage pattern. So if we're going to run into difficulties in constraining what the definition of a tornado is or isn't, are there things we can use in cases where there's a lot of ambiguity in terms of determining what the damage is, what the damage was caused by, that could help potentially clarify what was more likely to have caused the damage? So this is the how do we know part of this presentation. I'm going to focus on 2 things. I'm not going to focus on debris signatures. I'm not going to focus on circulations. I'm going to assume that we're thinking about cases that radar coverage may be poor or radar signatures may be a little ambiguous. And I'm going to focus on 2 other factors that could be potentially considered in determining what may or may not have caused the damage, whether or not it was tornadic or non-tornadic in nature. And so the first is going to be this idea of using the environment to help maybe sway a borderline case one way or the other. So going back to this idea from Atkins and St. Laurent as to how mesovortices produce damage, one of the keys here is the superposition of a rear inflow jet and descending rear inflow jet and the additional momentum added by that. So if you don't have, for instance, if you don't have a rear inflow jet, the case on the left in their figure from their 2009 tape, you notice that there's no descending rear inflow jet going into the back of that part of the line. And you notice that in the modeling, these mesovortices that formed were much weaker. They determined they were likely to be non-damaging in nature. So it's not just the presence of the mesovortex that's important to getting this non-tornadic wind damage mechanism associated with QLCSs and mesovortices themselves. It's really important to have the juxtaposition of the descending rear inflow jet. And this is supported by additional studies by Trapp and Weissman and observations by Wakamoto also from the Van X field campaign. So if we go back to what causes our rear inflow jet, right, and how we might be able to forecast rear inflow jet strength, this goes back to some of the follow-up work from RKW theory. So this is a paper from Weissman in 1992. And a key finding from Morris Weissman's paper is that stronger cape and stronger deep layer shear in his modeling simulations led to a stronger and more elevated rear inflow jet, right? And really, if you look closely at this graphic, which is the cape shear space and then the perturbation or the strength of the anomaly associated with the wind speed in the rear inflow jet, you notice that change jet are actually more closely tied if you look carefully at those lowest two rows, the lower Cape rows in the simulation, you notice that there's very little rear inflow jet development in lower Cape environments in the simulation, no matter the amount of shear or the change along the x-axis within those blue boxes. So the question that I end up asking myself out of all this is, if the rear inflow jet plays a critical role in producing wind damage associated with mesovortices even in QLCSs, how exactly does severe wind develop in, say, an HSLC, a high shear, low Cape environment? And so I'm going to show one example case to further illustrate this question and potentially some of my initial thoughts to it. This is a QLCS event, a pretty classical parallel stratiform event you see across North Alabama from mid-November 2017. Narrow line of storms. We had 3 radars operating during this event. You see the high top 80 HTX in Northeast Alabama, our fixed site C-band radar that we operate from UAH, placed at the Huntsville International Airport, and then our UAH MAX radar, mobile Alabama X-band radar, was located at a site northwest of Armour in the Tanner community during this event. This is a sounding launched about 30 minutes before the arrival of the QLCS to Huntsville. This is about as HS and about as LC as you're ever going to get, right? If you look carefully at the center, we're dealing with about 173 joules of mixed layer Cape, 247 surface base, so this is really, really low Cape. And if you look at the shear parameters, we've got 42 knots of 0 to 1 kilometer bulk shear and 60 knots of 0 to 3 kilometer bulk shear. So got impressively high shear and impressively low Cape for this scenario. I ended up on a survey team with the Huntsville office after this event, surveying 3 damage locations in northwest Alabama. There were 2 locations that were determined to be EF1 damage, EF1 tornado damage, and then one area that was ranked as non-tornadic wind damage, probably about 70 miles an hour in nature. So after that survey, it was done the day after the event. So I spent that was a Saturday event, Sunday survey. That Monday, I started pulling radar data from our radars, from Armour, from MAX, and then some stuff from high top. As I pulled the radar data and started comparing where the damage reports occurred to what the radars were seeing, you notice that over location after location was circulation, after circulation after circulation. You can see 3 circulations here from the Armour radar looking west, and the story just kind of kept being the same thing. Everywhere it seemed there were more substantial reports of damage. If you look at the radar, there were these little circulations showing up. So my advisor at the time, Dr. Kevin Nupp, and I spent over 100 hours in the field afterwards, after looking through this radar data. And this was a long, arduous process for us to do this, admittedly. But we found 12 additional swaths of greater than or equal to EF0 damage, and a couple of swaths that didn't quite meet EF0 criteria, largely associated with these circulations on radar. And you can see some of this damage was not insignificant. This was an auto parts store in the city of Florence. You can see some significant tree damage. This was some roof, large part of the roof covering removed off this church, more tree damage, and then a barn that was heavily damaged in northeast Alabama. And if you take a slice from our Armour radar, you cut a west-east slice through the imagery. First off, you notice that this was a very shallow system, about 20,000 feet. And the other thing you notice is that, indeed, there is no rear inflow jet whatsoever in this case. So if we've got damage that's probably reaching mid to high EF0, and maybe even in the case of that auto parts store and some of the tree damage getting into EF1, and there's no rear inflow jet to juxtapose with the mesovortex, the question that I have is, how did this damage all occur, if not necessarily by a tornadic circulation? And then for other, and by extension, for other high shear, low gauge QLCSs, how often do we actually have damage that's 70, 80 miles an hour in nature, even with the strong wind shear profiles and wind profiles that we had? How do we get this sort of damage to occur? Kind of close out this case, I've got storm relative velocity on the left and base velocity on the right. To kind of further emphasize this point, you may say, well, perhaps it's the mixing down of environmental momentum from that really intense environmental wind profile that you have. Well, if you look at storm relative flow, you notice that aside from the vortices, there's 4 of them actually kind of nested in the front part of that line there. Aside from those vortices, if you look at the rest of the cold pool, the storm relative flow is against the forward motion of the cold pool. So without the rear inflow jet present, you don't have an efficient mixing down of momentum from a loft. And so compare that to a high case. This is August 4, 2008. This is a classic progressive MCS in the Midwest. You can see that there's 8,500 joules of surface-based case, 8,800 mixed layer case from the Lincoln sounding here. So I play the opposite game in choosing these cases. If you do a slice through this QLCS, you see a very intense rear inflow jet signature, very clear. It's actually kind of elevated in nature. But if you look at, again, storm relative and base velocities, you notice that even aside from the mesovortices, you have more storm relative outbounds than we had in the November 2017 case, which again jives with this idea of mixing or combining some of the horizontal momentum transport from the rear inflow jet in association and adding in the mesovortex effect to give the absolute maximum in wind damage. So the environment could potentially play some role in helping determine what caused the damage, depending on exactly what intensity of damage and what the pattern of damage is that you're looking at. The other one, which I think is maybe a little bit harder to communicate, and I'll be honest, this is kind of me going into my own headspace at this point, but bear with me here, is the intensity of the damage itself. So say, for instance, you're out on a survey, right? If you're out on a survey and maybe you don't have any radar coverage, let's say your radar goes down, and the event occurs at night, if you come across a site that's EF5 damage, you're not going to say, well, it's probably straight line winds, right? And there's also this assumption, I think, that sometimes is made, and I've heard it, and this isn't accusing anyone of anything, but I know I've heard the assumption that, if it's an ambiguous case of damage, I don't have a real clear radar, I would handle it with a tornado necessarily. I need to be proven it's tornadic, and if I can't prove it, I don't have a preponderance of the evidence, it'll go down as wind damage or straight line wind damage. Right? But going back to the EF5 case, that same assumption is not going to apply. That same burden of proof isn't going to apply. And so the question I pose is, at what point, based off the intensity of the damage, does the underlying assumption that I have to prove it's tornadic not necessarily apply, based on how we currently classify damage? And so where I play fast and loose with statistics, and I'll get into the issues, of course, with storm data in a minute, is that I took all storm data tornadoes from 2006 through 2017 and all storm data wind reports. I lumped the storm data wind reports into the EF scale wind ranges, and I compared the incidence of documentation for the different EF scale categories. So EF0 obviously has a ton more wind reports than tornado reports, and then at EF1 that flips to about a 2 to maybe 3 to 1 ratio. So you can see once you get to EF1 damage, it's more common to classify your wind damage cause as being tornadic as opposed to being non-tornadic, right? And of course, like I said, storm data, this is really playing fast and loose with statistics given all the issues with storm data. Convective wind magnitudes are usually too high if they're estimated wind magnitudes, if they're not measured. If we apply a commonly used metric to try to reduce that overestimation bias, you notice that the transition becomes even more stark. Now you have a little bit less of a disparity in EF0 wind versus EF0 tornado, and way more EF1 tornadoes than EF1 winds. If you apply that estimated gust reduction to try to, again, remove some of that bias. Of course, there's many issues with the tornado record. If you've read Corey Cotton's paper published last year, you'll know that we may only be getting 45% of the tornadoes documented that occur in the southeast or central United States, which is a really fascinating, almost terrifying thought. And of course, there's issues with actually ranking the tornadoes based on whatever available PIs are out there given on any given survey. So with all these issues, these quote-unquote statistics must be taken with a grain of salt. But what we can say is that historical documentation of EF1 plus non-tornadic convective wind is far less common than documentation of an EF1 plus tornado. And this is where I get to using intensity as a potential way to figure out what might be causing damage. If you're on a damage survey, for instance, your radar coverage is poor, but you and you're not necessarily sure. It may have been a really fast-moving storm. You have a path of damage that's narrow, but the trees might all be falling towards the east-ish, or something, or all the debris may have been carried to the east. But say you estimate the wind speed to be 95 miles an hour, and you're asking yourself, well, was this a tornado or was this straight line winds? One factor you may wish to consider is that if you're defaulting towards straight line winds in an uncertain scenario like this, you'd actually be documenting an event that is much rarer to document in the official storm data than an EF1 tornado. So that's kind of where I'm getting at with using intensity as a potential defining metric for what is, or whether or not your damage is or is not tornadic in nature. And so to start wrapping this all up, what is a tornado and how do we know? And it may seem like I haven't come here with an answer to that question, or either of those questions, and that's because I haven't. I have absolutely not come here with an answer to either of those questions, or a definitive answer at least, or a new definition. And I'll explain why there at the end. All right, so to kind of tie all this up, what is a tornado and how do we know? It's not a secret or a startling new revelation, right? That this whole idea, this whole process of surveying QLCS is extremely complex. You can have numerous different mechanisms for causing QLCS damage, especially, and those mechanisms can be, coexist in close proximity or even overlapping with each other. You could have significant straight line winds and then have an embedded tornado track within there, right? I think many people have probably seen that example on a survey case in their careers. So the lack of a focused definition of what is or is not a tornado can even further complicate matters in determining the QLCS damage causality just by the broadness or the vagueness of the definition, right? So given that the definition of what is or is not a tornado is vague, and QLCSs can cause damage in different ways, and even mesovortices themselves can cause damage in different ways, we can start to use factors even aside from basic radar and damage interpretation to help in making a tornado no tornado determination. You could use the environment, whether or not it was a high CAPE or low CAPE environment, the presence of a rear inflow jet, and then of course, factor all that in with whether or not there was a mesovortex, whether or not there was a clear, longer, narrower path of damage associated with the QLCS at that time. and all that could then be linked together, and how strong the damage is, of course, whether or not whether it's like 60 miles per hour versus 80 miles per hour or 100 miles per hour could help bolster confidence in whether or not the damage was associated with a likely tornado. Kind of an aside in all this, I think this idea that I discussed in terms of using the environment and the idea of whether or not the momentum transport of just pure environmental momentum without a rear end force jet can be that efficient to cause significant damage in QLCSs really needs to be investigated to help even further help the environment be an even further better defining characteristic or clarifying characteristic as to damage causality with QLCSs. And finally, addressing the question posed by the June 30th event and whether or not we should more closely constrain or define the definition of what is or isn't a tornado. If we were to actually undertake this, right, we can't. I think it's been shown that we can't just jump into constraining a tornado definition. We have to make several considerations, right? Does the newly constrained definition have a basis in physical processes? Right. So that's kind of the, does it define the vortex? Does the vortex and what is the vortex define? Is that defined as a tornado or not? Is there a physical baseline for that? Are we just making an arbitrary assumption based on the intensity? Can the definition be feasible to implement operationally? So can all of you on the line going out on a survey later on in the future actually implement that definition within the constraints of what you have to work with from an operations perspective? How would the definition impact the tornado climatology? And this gets into the whole intensity question, what intensity using vortex intensity would do to the tornado climatology. Any definition we'd have to we'd be considering we'd have to consider whether or not it would be a massive earth-shattering impact to the tornado climatology like vortex intensity could potentially be. And then one that I'll just leave out there for all of you who actually work in the watch warning paradigm world is how would the watch warning paradigm be impacted? And I really don't have any answer to that question as somebody who doesn't issue watches or warnings. But in the end, and my final point is that such an effort would necessitate cooperation between physical scientists like me, operational scientists like yourselves, and social scientists to understand how any potentially constrained definition of a tornado would impact public perception of what occurred to them, how any impacts on the watch warning paradigm would impact public response, things like that, which is why I do not come here with direct answers to either of these questions, but I leave this as hopefully an opening to discussion in the community to start addressing some of these areas that lack clarity in what is a tornado and how we know QLCS events. And with that, I know with some of the technical difficulties, we're kind of running along on time, but if there's time for any questions, I'll take them.
Oh, very good. Thank you, Tony. I really appreciate the